Hello there guys, how's it going? Mike coming back at you here with another video on vector calculus. In the previous video, we saw several sample problems where we used the formula for the integral of a vector field along a three-dimensional surface S, aka flux in R3. We used that formula to solve several sample problems to see how we calculate the flux. In this video, we're going to talk about a big theorem, Stokes Theorem. We're going to get into the background of what we need to state this theorem. We're also going to go into the proof of this theorem as well. And then after that, we're going to see how this theorem relates to something that we've already seen in the course prior to this point. So before we state Stokes' theorem, we just need to give ourselves a little bit of a refresher on some stuff that we talked about previously, and we also just need to introduce some terminology and some notation. Line integrals are going to be playing into Stokes' theorem. So just a little thing to keep in mind about line integrals. When we talk about the line integral around the boundary of some enclosed region in the plane, we are going to assume that that curve is oriented counterclockwise. We are traversing a curve in a counterclockwise motion. And surface integrals, specifically the integral of a vector field over a surface, is going to play into Stokes' theorem as well. So just one thing to keep in mind, when your surface is just a function of two variables, the parameterization for that surface is really basic, really straightforward. Capital phi hat is u comma v comma f of u comma v. And that in conjunction with our vector field capital F hat, the flux of F hat across S is given by the double integral over d of p times minus the partial of f with respect to x plus q times minus the partial of f with respect to y plus r. And as mentioned in previous videos, we are working with the outward unit normal, and when our surface is a function of two variables, the outward pointing unit normal is the upward pointing unit normal. So that's just the couple small things we need to recap. Now we move on to some terminology and some other notation. So we see in our quick little sketch here in the bottom left of our screen, we have a couple curves and a couple things going on. So I'll get into a little bit of detail as far as what all this is saying. So the top curve that we have seemingly floating in XYZ space, picture that this curve, which I called partial S, lies on some 3D surface, capital S. And what this curve is going to do is that this boundary curve, partial S, is going to sort of close in some of the surface inside of this curve. Now, this boundary curve, partial S, we can define it by some vector function, which I called p hat of t. It is defined by x of t, comma y of t, comma f of x of t, comma y of t, where t goes from a to b. We are assuming that our surface is a function of two variables, x and y, so that's why we say that the z component is f of x of t, comma y of t. Now, if you remove the z component from p hat, you get the curve that is appearing on the bottom of our graph. It's appearing in the xy plane. I labeled this curve partial d, It is the boundary of some region D that is closed in by this curve. And we can define this curve, partial D, by the vector function c hat of t, which is x of t comma y of t. Again, t is going between A and B. So these two curves related to each other, they are going to each serve their own purpose, though, when we get into the proof of Stokes Theorem. Now, for the boundary curve partial S, we're still going to assume that we are going to traverse this curve in the counterclockwise direction. And when we traverse the boundary curve partial S in the counterclockwise direction, the outward pointing unit normal for our surface, S, is still going to be the upward pointing unit normal. This is the orientation induced by the upward normal n hat. This is the standard convention that we're going to work with. So unless the question specifies otherwise, you can assume counterclockwise orientation and upward pointing unit normal vector to our surface. So that's all the background notation and terminology that we really needed. We can now go on to the statement of Stokes Theorem. So what Stokes Theorem says is that let S be the oriented surface defined by a function of two variables, z equals f of x comma y, whose second partial derivatives are continuous, for x and y being in some simple region D. Now, when we talk about a simple region, we're just talking about something that's all one piece, and we can bound it by two relatively nice functions. This is not really a hypothesis or a condition that you're going to have to worry with. That's just some technical language in the statement of our theorem. Suppose we have a three-dimensional vector field, capital F hat, that has continuous first partials. And once again, partial S is going to be the boundary of S. It is going to be that portion of our surface that's enclosed by some curve. So if partial S is the boundary of S with the orientation induced by the upward normal n hat, then, and this is the conclusion of Stokes Theorem, it says that the double integral over S of the curl of F hat dot D capital S hat, also the double integral over S of del cross F hat dot ds hat, again, curl of a vector field is the same thing as del cross capital F hat, is going to equal the integral over that boundary curve, partial S, of capital F hat dot dr hat. So, a whole bunch of hypotheses there, but really what we're going to work with is the conclusion of this thing. We are going to show how we get these two quantities right here to be the same thing. So we're going to kick it off by working with the left-hand side. We're going to get that down to a certain point. Then we're going to work with our right-hand side, and we're going to see how these things simplify out. So kicking off with the curl of a three-dimensional vector field, if your vector field is capital F, which is PQR, the curl of that vector field is R sub y minus Q sub z, comma P sub z minus R sub x, comma Q sub x minus P sub y. So making that substitution into the left-hand side of our conclusion there, into the formula for the surface integral. Once again, keeping in mind that we're operating and we're doing this proof assuming that our surface is a function of two variables. We get r sub y minus q sub z, that quantity times minus the partial of z with respect to x, and so on and so forth. Then we multiplied the minus z sub x and minus z sub y in, and we wrote this all as one big integrand. Not the nicest looking thing, but it's all one integrand. So we're going to stop here for now, and now we're going to work with the right-hand side of our conclusion, and we're going to see how we get this down to the same thing. So we're looking at the integral over partial s of f hat dr, f hat dot dr hat, excuse me. That's the integral over our vector function p hat. So p hat goes from a to b. Our variable t goes from a to b in our vector function p hat. Taking the dot product of our vector field and the derivative of our boundary curve, we get the integral from a to b of p times dx over dt plus q times dy over dt plus r times dz over dt, and it's that whole thing times dt. This is just referring back to the line integral formula that we saw earlier on in this course. Now, z, as we said, is a function of two variables, x and y. So given the nature of the composition that we have to make, z is a function of x and y. X and y are both functions of t. We can talk about the derivative of z with respect to t, or dz over dt. By the chain rule that we talked about earlier on in the course, dz over dt is equal to the partial of z with respect to x times the derivative of x with respect to t, plus the partial of z with respect to y times the derivative of y with respect to t. So what I'm going to do is I'm going to take this whole thing right here, and I'm going to substitute that in for dz over dt in the line above. And you can see that when we do that, we get the integral from a to b of p times dx over dt plus q times dy over dt plus r times everything that we just underlined. We multiply the r into both of these terms, and then we're going to just reorder some terms. We're going to regroup terms that had a dx over dt in them, and we're going to then regroup the terms that had a dy over dt in them, and we're going to pull out those common factors in those respective groups of terms. That gets us to our last line on the last part of our first line here. We can multiply both terms in there by the dt, and the dt's cancel out. Now, this is an integral of two pieces. This is now just the x and the y. We have now completely removed the z piece to this, so we're not taking the integral over the boundary curve partial s. We're taking the line integral over the boundary curve partial d. So we now get the integral over the boundary curve partial d of some stuff times dx plus some other stuff times dy. This is what we get in the last part of our second line here. Now think of everything in here Think of this as just a fancy p, and think of this as just a fancy q. The integral over some curve of p dx plus q dy. This looks like a line integral, as we would think it should be. But we can use Green's theorem now to see what this is going to look like as a double integral. So by the circulation curl form of Green's theorem, the integral over partial d of p dx plus q dy is equal to the double integral over the interior of that boundary, or the double integral over d of the partial of q with respect to x minus the partial of p with respect to y. That's what the circulation curl form of Green's theorem is saying. So when we apply this to this integral that we have here, we get the last part of our next line here. We're taking the partial of q plus r times partial of z with respect to y. We're taking the partial of that thing with respect to x, and then we are subtracting from that the partial of p plus r times partial of z with respect to x, the partial of that with respect to y. So now we have some partials to calculate. We have some product rules to kind of work with here, and we're going to see what this turns out to be. We get the partial of q with respect to x, and also, because this is a chain rule, q is a function of x, y, and z, but z is a function of x and y. So when we take the partial of q with respect to x, we are using a chain rule there. So we get q sub x plus q sub z times z sub x. And then we get r times z sub yx plus, and now again when we differentiate r with respect to x, we are doing another chain rule there. So we get r sub x plus r sub z times z sub x, that whole thing times z sub y. So that's everything we get as a result of differentiating the first piece here with respect to x. I know, that's a whole bunch of fun stuff. So exciting. Anyway, differentiate the entire second term here with respect to y. Again, differentiating the p with respect to y is going to be a chain rule happening there. So we get p sub y plus p sub z times z sub y, plus r times z sub xy, plus the partial of z with respect to x times what we get when we differentiate r with respect to y. That is another chain rule that's going on there. So we have a whole bunch of terms here. We need to multiply things in. We need to begin to simplify things out. So just as a result of multiplying the z sub y in and the z sub x in, we arrive at this line right here. Now we begin to look and see as far as where can we begin to cancel things out. So if we take a look at this integrand right here, I see that we have a r times z sub yx, and we have a minus r times z sub xy. Well, by Clairaut's theorem, mixed partials are equal. So these two terms are the same, and I'm taking one and I'm subtracting it from itself. So those terms are going to go out. And then also I look in here and I see that I have a plus r sub z times z sub x times z sub y, and I have a minus r sub z times z sub x times z sub y. So those guys will cancel each other out as well. That is all that we can cancel out. And that leads us down to the double integral over d of q sub x plus q sub z times z sub x plus r sub x times z sub y minus p sub y minus p sub z times z sub y minus r sub y times z sub x. And what we find, if we go all the way back up to the beginning of our proof, we find that this is the exact same thing as what we found when working with the left-hand side of our conclusion. So, this completes our proof. We have shown that these two things are equal. Now, in the grand scheme of things, I'm not going to be so concerned as to can you repeat this proof back to me, but this is the kind of thing that you should be pushing yourself to kind of understand why these things are what they are, why we're doing what we claim we can do, and just being able to follow with our proof and saying, okay, we're doing this because of this, okay, that makes sense. We're doing this thing next because of this, okay, that makes sense. Just being able to follow through these proofs that we are doing and being able to understand why we're doing what we're doing is enough of a challenge. So I really do want to push you all to really try to follow with me when I go through these proofs, and I want to push you to understand why it is we're doing what we are doing. Now, we've done all this stuff assuming that our surface was a function of two variables. We have a very similar, in fact, the same formula in case our surface has to be parametrized in terms of u and v. Same thing. There's just a little bit more work that we have to do, but for the most part, we are going to be sticking with surfaces that are functions of two variables. So this is just a bit of an intro into Stokes Theorem, the background behind it, the statement of the theorem, the proof of it, and then what this is really telling us, and how we have seen this thing before, just in a slightly different format. If you have any questions or comments, be sure to drop them in the comment section below. Otherwise, guys, until the next video, take it easy.